everyone, my name is Tiankang Su. I am from Nanjing University of Information Science and Technology. I am very glad to have this opportunity to attend the latest international conference on computer vision. The topic of my presentation is unsupervised video object segmentation with online adversarial self-tuning. I will introduce our work from these four aspects. Project overview, existing problems, proposed methods and experiments. Project overview. The task goal of unsupervised video object segmentation is to segment foreground targets at the test time without any prior knowledge. There are a lot of challenges in UVOS, such as illumination variation, severe deformation, heavy occlusion, scale changes, motion blur and low resolution. Besides, there are also numerous applications in real world. For example, object tracking, video edit and automatics driving. Existing problems. The existing unsupervised video object segmentation methods depend heavily on the segmentation model trained offline on a labeled training video set, and cannot well generalize to the test videos from a different domain with possible distribution shifts. The examples are shown in Figure 1. To address this, we propose to perform online fine-tuning on the pre-trained segmentation model to adapt to any ad hoc videos at the test time. To achieve this, we design an offline semi-supervised adversarial training process and online self-supervised adversarial fine-tuning. Proposed methods. Overview of our OAST method. In the offline semi-supervised adversarial training stage, given a labeled video frame and any unlabeled video frame without using test data and together with their optical flow map as input, our base segmentation model outputs two segmentation masks for each. A discriminator is trained in an adversarial manner such that the feature maps from the labeled and unlabeled frames become distinguishable. In the online self-supervised fine-tuning stage, a teacher model and a student model are initialized with the trained base model weights. Given a test frame together with its optical flow map, we use the teacher model to generate an augmentation, averaged prediction as the pseudo-label, while using the student model to generate a predicted map on the raw frame. The two masks are fed into a discriminator to minimize the gap between the teacher and student model. The student model is updated online by adversarial learning over each test frame, and the teacher model is updated by the student model weights using exponential moving average. Finally, here are our experiments. We list the results on Davis 16 and FBMS test sets for UVOS, and the numbers in red, blue, and green indicate the top 3 performance. It is clear that our approach achieves the most competitive result compared to its counterparts. We list the results on Davis 16, FBMS, DAVSAT, 6-cell and MCL datasets for video salient object detection, in which the numbers in red, blue, and green color indicate the top 3 performance respectively. From the results, we can observe our OAST almost achieved the best performance compared with other methods. We show the exemplary segmentation results over test videos. We can see that the cat and horse objects in the first 3 rows can be precisely segmented even when their appearance and background evolve significantly over time. Meanwhile, the worm, black swan and cheetah objects in the last 3 rows are also perfectly segmented even they are novel unseen categories from the training data. The first column of the figure shows the distribution shift matrix between the Davis-16 and the unlabeled data with and without adding unlabeled data for offline adversarial training. The last two columns visualize the feature distribution with and without unlabeled data over Davis-16 and unlabeled data. As seen, the model trained with unlabeled data exhibits a distribution shift metric of 0.23 between Davis-16 and the unlabeled data, significantly smaller than the model trained without unlabeled data. Furthermore, the feature distributions become much closer, indicating that adding unlabeled data via offline adversarial learning has effectively reduced the distribution shift. Thank